So thank you so much for being here today and taking some time out of your day to hear a little bit about some of the exciting science that you can do with dwarf galaxies that are around our Milky Way galaxy. And in particular, how this view has changed since the advent of all-sky astrometry that has been provided by the Gaia satellite. So this over here, I'm going to try and use the zoom pointer. This over here is an image of the whole sky with the Gaia satellite. It's not an image in the traditional sense where you're counting photons. It's actually essentially a weighted histogram of the number of sources on the sky. There's about 2 billion stars inside of this map. I think Gaia, the mission, was basically mostly constructed to study this thing in the middle over here, which is our Milky Way galaxy. But you can see that there's other objects inside of this map as well, right? So over here are the large and small Magellanic clouds. In the northern hemisphere, I have to tell people what those are. Down here, less so. And so these are dwarf galaxies around the Milky Way. Individually, they're less than 10% of the mass of the whole Milky Way, so they're relatively small. But there's actually dozens more galaxies that are in this image. There are stars in this image. They're just too faint. They have too few stars to actually see directly. So these are the large and small Magellanic clouds. There's tons more Milky Way satellites around here. They're in the map. They're just too faint to see. So let's take a look at where they actually are. This is going to be a video that's it's going to spin around. That's just to give you a 3D view. Our Milky Way disk is right over here in the middle. It's about 15 kiloparsecs radius. And what's shown here, the large extent is the extent of our dark matter halo out to the virial radius of 300 kiloparsecs. The large and small Magellanic clouds, you can see with the naked eye as wonderful overdensities in the plane of the sky. And what happened over the course of the last centennium or so is that we've begun discovering other dwarf galaxies around the Milky Way. So the first dwarf galaxies we discovered looked like this. Everyone always looks at this and thinks that the galaxy is this bright thing over here. That's actually the star Rigel. But indeed, the dwarf galaxies we're looking at, Leo 1, is sort of at the outskirts of our Milky Way. And you can see that it's actually resolved into individual points over here. So these dwarf galaxies, one of the reasons we like studying them around the Milky Way is they're resolved into individual stars, which means we can actually take photometry of individual stars, take spectra of individual stars, and reconstruct the histories of these individual dwarf galaxies. If you were paying attention to the video while I was talking, you might have also seen a whole bunch of points appeared around 2005, and then a whole bunch more points appeared in the southern hemisphere. This was basically due to the advent of deep, wide, and all-sky photometry. To sort of show this a little bit more quantitatively, the x-axis on this plot is the year that a dwarf galaxy was discovered, and the y-axis is the cumulative number. And what you can see is that, for about 100 years, I keep saying decade, for about 100 years, we had, we're discovering galaxies basically through photometric plates looking for ovodensities on the plane of the sky. But once digital sky surveys came around, we sort of had a huge uptick in the number of galaxies here and then again over here. So this was the Sloan Digital Sky Survey around 2005, and this was the Dark Energy Survey around 2015. And the reason for this discovery was basically we got extra dimensions to search for dwarf galaxies in. So this is an image of my favorite galaxy in the universe. It's not the Milky Way, it's this thing over here. If you stare at it for a little bit, you will be very confused because it just looks like a bunch of random stars in the sky. And indeed, in the plane of the sky, this is just nothing, right? It's not an overdensity. It just looks like every other patch of the sky. And that's because there's so many stars inside of our Milky Way, inside of the foreground, which are basically drowning out the galaxy. What you can do with deep wide photometry is essentially do a three-dimensional search, adding the distance dimension by scanning in the color magnitude diagram. When you do that, this thing basically pops out. So it's an overdensity in 3 dimensions, but it's not an overdensity in 2 dimensions in the sky. OK, so we have something like 50 or 60 dwarf galaxies around our Milky Way today. Where do they actually come from? So this is a dark matter simulation of the assembly of a galaxy like the Milky Way. The color over here is going to be dark matter density of different halos, and the yellow and red points are basically where some of the first stars and galaxies in the universe form. The center over here is the virial radius of the proto-Milky Way, starting at right after the Big Bang, basically. So over time, you form all sorts of little stars and galaxies in the volume that is eventually going to become the Milky Way, right? These things, they form, and then they accrete over the next 14 billion years to form our Milky Way galaxy. The things that form, that sort of accrete the earliest end up forming this big blob of material over here. That's called the stellar halo of our Milky Way galaxy. And it's formed from the tidally disrupted remnants of hundreds and hundreds of little dwarf galaxies. Things that sort of accrete at intermediate times, you might have seen this thing over here. They basically accrete into our Milky Way and get tidally disrupted, but maintain their physical shape for a while. That's called a stellar stream. You can still see it as a coherent structure in the plane of the sky, in physical space, but instead of being sort of phase mixed. And the 60 dwarf galaxies that we know of around the Milky Way today, they're basically these sort of recent accretions, things that have fallen in at the most recent times, and so they're still intact and have not yet been tidally disrupted. And so if you look at the physical state of a galaxy today, whether it is intact, that means it fell in most recently. It's in a tidal stream, that means that it fell in at sort of intermediate times. And then the earliest accretion events are fully tidally disrupted and make up the stellar halo. So there's a correlation between the accretion time of a galaxy into our Milky Way and the physical state of it today. OK, so now there's lots of these dwarf galaxies. What can you actually do with them? There's many different things. Hopefully you find at least one of these things interesting. One of them is you saw that these dwarf galaxies form at the very beginning of the universe. That makes them especially good probes and essentially record keepers of the formation of the very first stars inside of the universe. Because they're these very low mass galaxies, they're very interesting from a galaxy formation perspective. They let you study things like supernova feedback and reionization and the impact that it has on things going to far lower masses than you could study in the rest of the universe. Because these galaxies are so close, we resolve their individual stars, you can actually take a spectrum of individual stars with actually quite high resolution spectroscopy, R of 30,000 spectroscopy. And through that, you can study nucleosynthesis, which of course is the origin of the elements, as well as chemical evolution, which is the buildup of these elements over time. And then finally, by measuring sort of the actual kinematics of the systems, you can study galactic dynamics and dark matter. So that's both the motions of the stars within the dwarf galaxies themselves. That tells you about the density profile of the dwarf galaxies themselves, as well as the motions of those galaxies around the Milky Way itself, which tells you about the galactic potential overall. So my research group at University of Chicago, we're basically studying all of these different topics in different ways. And today I want to focus on sort of the right-hand side of this, and in particular, the fact that we got kind of limited when studying these dwarf galaxies. So there's like 60 of them around the Milky Way. But then you say, OK, well, we did all 60 of them. Then what do you do next, right? And so this is a real limitation if you're interested in these nearby dwarf galaxies. We just ran out of them to study. But there's a lot more dwarf galaxies that are not intact, which are in fact tidally disrupted, and we just can't find them as a blob of stars because they've been accreted at an early time and been ripped apart by the Milky Way's potential. And the thing that allows us to, in principle, they're here. We just have to recover and find them. And the thing that really allowed us to find and discover and study these galaxies is the advent of Gaia. So Gaia, someone once told me this looks like a trash can, and I've never been able to unsee it ever since. It's a satellite that's out at L2, and it's constantly spinning. And as it sort of goes around, these two cameras basically give it extremely precise measurements of the location of objects in the sky, right? And as this satellite sort of processes around, it'll hit the same point on the sky at different times. So that's sort of this location right here. And what it does is give you multiple measurements of the positions of stars over a long period of time. And as all of you know, this then lets you measure basically the proper motions of stars, which is the net motion of the object in the plane of the sky over time, as well as the parallax, which is the yearly motion of the Earth going around the sun. In other words, it gives you 5 of 6 phase space coordinates per star, right? You get the position of the object on the sky, that's the 2 angular positions. You get the proper motion, that's 2 velocity coordinates, as well as the distance, which is the parallax coordinate. So the last one, of course, is the radial velocity. So for those who don't yet know that Gaia is amazing, this cartoon, I think, sort of illustrates how amazing it is. So prior to Gaia, the last all-sky astrometric mission was Hipparcos, and that basically gave us a useful sense of information out to about 100 parsecs, which is really just in the solar neighborhood. Now with Gaia, we basically can go about 100 times further with sort of similar quality data. And so this really lets you study a substantial fraction of our entire Milky Way galaxy and even out into the halo. And the thing that, when I first heard about Gaia, I was like, oh, I'm never going to care about Gaia. It's only interested in things within 10 kiloparsecs, and everything I care about is outside of 10 kiloparsecs. So that was really dumb, because it turns out, of course, the thing that matters is how bright the star is, because if you have a very luminous star, that can, of course, be seen out to much farther distances with similar fidelity. And so indeed, Gaia can actually easily reach out to the virial radius of our Milky Way if you just look at the most luminous red giant stars. And even if it can actually measure things all the way out to Andromeda galaxy if you look at the very most luminous stars in that system. So it's really actually quite extraordinary and has given us many more dimensions to study the local volume in. So from the perspective of dwarf galaxies, I think this sort of is an increasing sequence of dimensions to discover dwarf galaxies in. When we just had two dimensions to search for dwarf galaxies over densities on the plane of the sky, that allowed us to discover the most luminous dwarf galaxies around the Milky Way. When you add the extra dimension of distance through all-sky photometry, you end up being able to find the relatively low mass and faint dwarf galaxies. Now with Gaia, by adding these extra kinematic properties for each of our stars, we can actually search for overdensities in 5 dimensions, adding proper motions and getting better distances than we could before. This lets us study dwarf galaxies in the act of tidally disrupting, in particular stellar streams. And then finally, adding spectroscopy, this gives us at least the radial velocity direction, as well as at least 1 dimension of chemical abundances, and really much more. And what this lets us do is go back and study the tidally disrupted dwarf galaxies, the very first things that are created into our Milky Way, and distinguish them from each other. So that's sort of the introduction here. So Gaia has overall just really revolutionized our ability to discover dwarf galaxies and also characterize those systems. And what I want to tell you about today is sort of 2 examples of dwarf galaxies that were kind of discovered in the Gaia era, and sort of the wonderful different types of science that you can do with dwarf galaxies that have been found. I'm first going to talk about galactic dynamics with a dwarf galaxy that's called Antlia 2. And then I'm going to talk about the origin of the R-process nucleosynthesis with a dwarf galaxy called Gaia Sausage Enceladus. What you will have realized is that what you will learn is that people just like giving names to galaxies, and in this wonderful age of discovering lots of different things, they can name them whatever they want. So that's what happens. OK, so let's start with galactic dynamics with this dwarf galaxy called Antlia 2. And to sort of, by way of introduction, this over here is a plane of all of the satellites around our Milky Way that were known in sort of 2019. The x-axis over here is the size of the object, going from small to large, and the y-axis is the luminosity of the object, which is basically how many stars are inside of the galaxy, right? So you can ignore these things over here. Those are the globular clusters, interesting but a different talk. I want you to focus on the blue objects over here. These are dwarf galaxies. They sort of follow this luminosity size relation. And when I was a graduate student, which now is impossibly long ago, what I was told by various elders was that we have found all of the dwarf galaxies around the Milky Way with above 100,000 solar masses, right? We've searched the whole sky. There's nothing that's going to be this faint. So you should look for the low mass dwarf galaxies if you want to study those. So I happily did that for 5 years. And then I looked at a plot like this and realized this was a terrible, silly thing to say, because the thing that actually controls whether or not you discover a dwarf galaxy is the signal relative to the background. And what you can imagine is, the signal of a dwarf galaxy is how many stars are in there. That's why they said more luminous galaxies are easier to discover. But the background depends on how large that object is on the sky, because your background is coming from Milky Way stars. And so what this means, basically, is you could have missed any galaxy that was very luminous, had lots of stars, but spread out over a very large area on the sky, right? So this is called a low surface brightness galaxy. And indeed, the galaxy I want to tell you about today, Antlia 2, is, I think until about a month ago, the most lowest surface brightness galaxy that was known inside of the universe, discovered in resolved stars. So this Antlia 2 dwarf galaxy, when it was discovered, they named it this wonderful thing, the hidden giant. So I'll start with the giant part of its name. This object in the plane of the sky, this x-axis, so here's the object over here. It's an overdensity of stars. The x-axis is in degrees. This thing, its half-light radius, like physically on the sky, is as large as the Andromeda galaxy. And so, yeah, and for comparison, here's the full moon, right? So this thing is just absolutely ginormous. It's large on the plane of the sky, but it's also actually large physically. So it has the same physical half-light radius as the Large Magellanic Cloud, but it only has 1/1000th as many stars. So this is just huge in every way you could imagine it, physically large. A galaxy like this is hidden because it's actually at a galactic latitude of only 11 degrees, which means it's quite close to the galactic plane, and so there's tons and tons of Milky Way stars in front of it. But fortunately, all of the stars in the Milky Way are sort of going around in a circle, right? And that means that from our perspective, they have some net proper motion. Whereas this galaxy over here, it's about 130 kiloparsecs away. It has a small but non-zero proper motion. And so you see an overdensity of objects at these very small proper motions along at a particular distance. So this object was really identified and characterizable due to a 5-dimensional search for this object. So things like this are kind of confounding. It turns out it's very difficult to get objects that are low mass and large inside of lambda CDM. Sort of alighting over the details over here, there's basically two things that need to be true in order to explain it with our standard theories of galaxy formation. The first is that it has to be tidally disrupting. That's basically what allows it to puff up to this large size. And the second thing is that it has to live inside of a Corge dark matter halo. Both of these things essentially have to be true to produce a galaxy of this size. So today I'm just going to focus on the first part over here. Is this galaxy tidally disrupting? And ask if we can show that observationally. So what is the signature that we should actually see? This is a simulation by Dennis Urkel. The red over here is just some background dark matter particles from our Milky Way galaxy, and I want you to focus in on this little green thing over here. So this object, as it orbits around our galactic potential, is going to tidally disrupt. What that means is it loses particles through the two Lagrange points, of course, right? Some of these particles have a little lower energy. They're a little bit ahead on the orbit, and some particles are behind. They're a little behind on the orbit. So this object, as it's tidally disrupting, the stars that it's lost and the stars that it's lost sort of trace out the orbit of this object inside of the gravitational potential, right? And so if this was our central remnant and it's tidally disrupting, we should see some stars over here, and they should essentially be a little bit ahead on the orbit. And we should see some stars over here, and they should be a little bit behind on the orbit. What this manifests as is a velocity gradient, right? Because if your object is going out towards its apocenter furthest distance, the stars are going to be slowing down. And so the stars in front will be slower relative to the stars in back, and vice versa if it's coming back in. So what we want to do is measure a velocity gradient. You can't do this with proper motions because they're not accurate enough. And so instead, what you have to do is actually take spectroscopy of all of the stars inside of this system. And so that's what we did, and this is one of the big reasons I'm in Australia. The collaboration that I'm a part of is the Southern Stellar Stream Spectroscopic Survey, or S5 for short, because that's impossible to say. This is a collaboration of many people who are essentially going after every tidally disrupted object in the southern hemisphere, the southern sky, I guess, from the Anglo-Australian telescope. And the wonderful thing about the Anglo-Australian telescope is it has this huge field of view, 2 degrees in diameter. And that means that even though this object is as large as Andromeda on the sky, you can cover out to 2 half-light radii with just 5 pointings. This is totally impossible with basically any other large telescope. Each pointing is about that size, and you have to integrate quite long as well. So this is there's no other system like in the southern sky that has sort of a similar field of view and is able to get enough object spectroscopy at once. So we take spectra of all of these objects, we measure their metallicities and radial velocities, and so we'll just jump to the point here. This over here is a map of the member stars in our system. The big circles are stars that are basically proper motion members, velocity members, metallicity members. They're just inside of the galaxy. What we should expect to see, I've colored them according to their line of sight velocity. where blue means it's going away from us and red means it's going away from us faster. And so what you expect to see if you want a velocity gradient is that you should see a color gradient across this system over here. And indeed, you just see it by eye, right? This is like a huge velocity gradient across this system that, yes, indeed, there is this. So there is a velocity gradient, but that's actually not a unique explanation. If you think about galaxies that are rotating and then you project them into the line of sight, you also expect to see a velocity gradient like this as well, right? Normally, when we're outside of the Milky Way, this is a perfect degeneracy. We can't tell whether something is disrupting or rotating. But in the Milky Way, we have the proper motion of the system, which is this purple vector over here. This black vector points in the direction of the positive velocity gradient. And these things are aligned exactly in the direction that you would expect if this object is tidally disrupting, right? So just qualitatively looking at comparing these two vectors, you can argue that this system is tidally disrupting. Now, of course, we didn't just do that. What you would like to do is run a model of tidal disruption for the system and show that it indeed is tidally disrupting. And so that's exactly what we did. And I think for those who haven't played with galactic dynamics before, this is usually a very finicky process. There's a huge number of parameters of things to initialize, and you set things up, and it basically never works. And so you play around with your parameters for a bit, and then it can work out. This model over here was the second model that I ever ran. The first one was because I crashed the model because I had my units wrong. But this is the second model that I ran with just putting in all of our measurements of the system inside of our standard galactic potential, no fine tuning whatsoever, right? And so the blue contours are contours of stars from our model of this tidally disrupting system. And you can see that it basically almost perfectly reproduces the physical orientation of the system, comparing the blue to the dash points over here. And it also actually basically perfectly reproduces the velocity gradient that we see over here. So I think this, the fact that there's no fine-tuning needed in any of this is extremely good evidence that this object is in fact tidally disrupting. And so it is plausible that you could produce a system like this in lambda CDM. Great, so this is what it looks like now, but it turns out I want to show you how amazing this Gaia data is. So I didn't notice it when I first looked at this, but it turns out there is a very small disagreement here. If you look at the orientation of this blue set of model points over here, and you look at the orientation of the actual object, which is this dash contours over here, you can see that they're slightly rotated relative to each other. It's only by about 15 degrees, 20 degrees. It is statistically significant. It's like 2 or 3 sigma. And this turns out, we think, to actually be a signature of the fact that our Milky Way and Large Magellanic Cloud are interacting. So what does this mean, right? So we live inside of our Milky Way disk, and that giant galaxy that we saw in the very first image, the Large Magellanic Cloud, it's coming in on its first infall into our galaxy. And so the same way that two stars orbit around a common center of mass, when the Large Magellanic Cloud comes in, it's not significant at the outside. It's about 20% of the mass of the Milky Way. But as it comes into the middle, it and sort of the center of the Milky Way co-orbit around a common center of the mass, similarly to how binary stars or planets and stars orbit around each other. And so this is a simulation showing of what we expect to happen. This is the Milky Way disk. We live over here or so, or I guess over here. And as the Large Magellanic Cloud comes in, it sort of comes close about a gigayear ago and then orbits back out. And our disk actually moves by about 20 kiloparsecs from where it used to be. So we, 2 gigayears ago, were 20 kiloparsecs or so the center of the disk has moved by about that much, right? Just due to the fact that the Large Magellanic Cloud has come in and we're orbiting around. So this in of itself, I think, is extremely cool. From the purposes of this talk, what matters is that in addition to actually physically displacing us, we are moving down in this reference frame at about 30 kilometers per second. And so in the same way that when you measure a velocity of a thing, you have to correct for the fact that the Earth is rotating, and then the Earth is going around the sun, and then the sun is going around the galaxy. And when you do all of those corrections, we now have to add an extra correction over here, which is the fact that our whole galaxy is going around the Milky Way LMC, common center of mass. And so it's about 30 kilometers per second down, or a redshift of 10 to the minus 4 for people who use those units. So what does this do to the Antlia to Dwarf galaxy? And so this, again, is a model where we've run with no fine-tuning. We literally take measurements of the Large Magellanic Cloud's proper motion and its mass from other constraints, and then we just look to see what it does for this little galaxy. So I want you to focus on this right plane over here. This is rotated so that Antlia 2 is going to orbit inside of the plane over here, conserving angular momentum, right? And so what happens is, as the Large Magellanic Cloud comes in, it's going to pull. So it's going to come in around now. There it is. It pulls our Milky Way down as it gets close to the center. And then as it's orbiting out, this sort of changes a little bit. And the dashed line over here is sort of the actual orbit of the system on the sky. And the blue over here is essentially the tidally disrupted particles emanating from the system. And you can see that normally, in the absence of something like the Magellanic Clouds coming in, those two things would always be aligned. But because the Magellanic Cloud has pulled us out of the way, there's a velocity offset where it's actually going in this direction, even though the stream is aligned in this direction. So you can take that model and compare it to the actual data. So again, this is the model I showed before, where you have the Milky Way center just sitting there being fixed. It fits pretty well, but there's a small misalignment here between the direction of the blue lines and this black over here, which indicates the orientation of the object on the sky. Once you include the fact that the Large Magellanic Cloud pulls the Milky Way out of place, you get this red contour over here. And you can see that it's not perfect, but it's very well aligned with the direction of the actual tidally disrupting galaxy on the sky. And indeed, quantitatively, there's a better fit to the velocity gradient over here as well. So that's the first part of my talk, which is that there's this dwarf galaxy, Antlia 2. It was discovered in essentially a 5-dimensional search through Gaia. It's tidally disrupting, which means that we could be explained in standard galaxy formation theories. And also, its detailed kinematics shows that our Milky Way and Large Magellanic Cloud have been interacting over the course of the last 2 billion years. So I'm going to pause and ask if there's any questions about this last section on galactic dynamics.
The motion of the Milky Way, that must be relevant relative to the cluster center of motion or something like that?
Yeah. So it's some super inertial reference frame. You can decide. It's very hard to define static reference frames, right? You can even define it in this case relative to the outer part of our Milky Way's halo. So if you look outside of about 100 kiloparsecs, it's essentially unaffected by the Large Magellanic Cloud. It's only a small mass perturbation. So it's only the center of the Milky Way sort of sloshing around relative to the outside of it. So if you care about things only within about 30 to 50 kiloparsecs, you don't care about this, right? The dynamical times are too short compared to a few gigayears. So if you care about the disk, this doesn't matter, except that it's cool. If you care about anything outside of about 30 to 50 kiloparsecs, including redshift, including things where you measure distances in redshifts, then actually this is a substantial effect. It's a real effect. It's 10 to the minus 4 in redshift, so I don't know if you care. But it does exist. So it's most relevant for things sort of in the outer halo or in the local volume where you care about up to a 30 kilometer per second difference. Any other questions about this before I change topics? Cool. No one's going to ask me about chord density profiles. You can ask about that later. OK, then let's move on to the next topic. So I'm going to switch gears. I've talked about sort of galactic dynamics and a little bit about galaxy formation. Now I want to talk about the rise of the R process in this dwarf galaxy, Gaia, Sausage, Enceladus. I'm going to go through this in a couple of parts. First, I'll talk about the R process. Then I'll talk about what we see in this dwarf galaxy, Gaia, Sausage, Enceladus. And then finally, I'll get to the rise itself. So taking a step back, this over here is the periodic table of elements, color-coded by roughly in our solar system where those elements are made cosmically, right? And for the purposes of today, what I want you to focus on is these orange squares over here. These are elements made in something called the rapid neutron capture process. And the basic question is we have been arguing for 70 years, which is older than me, about where these elements actually get made inside of the universe. So why have we known about the fact that these elements get made for 70 years? It's due to the fact that we understand, in some sense, we understand what nuclear physics processes are responsible for producing this particular set of elements. And the idea over here is you start with some seed nuclei. This is some ironish nuclei. You begin hitting them with a whole giant number of free neutrons. What happens is these nuclei, they capture neutrons, they move all the way to the right on this plot. And then once the neutrons are used up, then they beta decay back to this valley of stable isotopes. I guess I should have said this over here, the x-axis, this is a chart of the nuclides. The x-axis is the number of neutrons in a given atomic nucleus. The y-axis is the number of protons, which is different elements. If you take a nucleus and you add a neutron to it, you're going to move 1 square to the right. And then if a neutron beta decays, you're going to go 1 square up and to the left, and that's turning a neutron into a proton, right? So I'm going to play this again, because, and I want you to pay attention to the time scale over here. So this entire process happens over the course of just a few seconds. Right, the neutrons get used up in about a second, and then they beta decay back to this valley of stable isotopes over here. So it's quite an extreme process, and in some sense this makes sense because free neutrons are unstable, they decay, right? And so you have to, it's very hard to get a very large number of free neutrons. And then the other thing that you'll notice is that there's these vertical bars over here. These are the magic neutron numbers. They're similar to closed valence electron shells. Essentially, it's a little harder to go beyond one of those bars. And so when you do this R process, you sort of pile up at these 3 locations over here. And when the beta decay happens, you produce 3 characteristic abundance peaks. And so that's sort of, when you look at the solar system isotopes, we basically see these 3 abundance peaks. And we saw that 70-ish years ago. OK, so how do you actually get something like this to occur? You need a lot of free neutrons, and the only way we know how to do this in the universe is ripping off material from a neutron star. So you can either do this in the birth of a neutron star or the death of a neutron star. So the birth of a neutron star is a core collapse supernova, right? Your 1.4 solar mass iron core collapses, turns into neutrons, emits 10 to the 53 ergs of energy of neutrinos. In that process, you might eject some of the neutron-rich material, in which case that could turn into our process elements. The other way you can do this is a neutron star merger. That's, in some sense, the death of a neutron star. You have 2 neutron stars, or a neutron star and a black hole in a binary. They in-spiral through gravitational radiation. And then eventually they merge, tidally disrupt the neutron star, which is made of neutrons. And that gives you some neutron-rich material that could turn into the R process. So I literally could have spent the entire talk going through some of the interesting things about this. To summarize decades of work, broadly, what we know from past observations is that R process sites are rare and they're prolific. By rare, I mean that they're rare compared to a regular core collapse supernova. So you get about one of these things about every 1,000 regular core collapse supernova. And by prolific, I mean that when they happen, they produce a relatively large amount of R process. In this case, large means a few % of a solar mass. And so it's a relatively small amount of total metals, but a lot for these types of elements. This type of general analysis is able to rule out certain types of ways we might be able to produce our process elements, but it basically leaves everything else open. And indeed, the most basic question you might ask is, does the R process happen in core collapse supernova, or does it happen in neutron star mergers, and which of them is more important over cosmic time? Just sort of to give my own personal opinion on this, where we are right now is that the supernova are theoretically promising, but to this date, we actually have no direct observational evidence, or even, in my opinion, indirect observational evidence that this ever happens. It's not clear if supernova could ever make our process elements. In contrast, neutron star mergers, of course, they definitely do happen, and they definitely do make our process. And the poster child for this is this event, GW170817. This was a wonderful multi-messenger event where there was a triple coincidence of gravitational waves. That's this plot over here. This is the frequency versus time, and this color coding the strain. You can tell that it's a neutron star merger because this whole thing lasts like 30 seconds as opposed to a couple of seconds. So we saw a merging neutron star, a pair of merging neutron stars. We actually also saw a very weak gamma ray burst. And then people went and searched through all of the different galaxies in this little region over here, and they found that dot. This dot is the kilonova. Unlike a supernova, which is powered by the decay of nickel-56, this transient over here is powered by the radioactive decay of our process elements. So that beta decay part over there that we saw on the other thing is sort of what provides the energy for this transient over here. So now it's been 7 years since this event happened, which seems like not that long ago to me, but I guess has been. And I think this definitively proved that neutron star mergers happen, and they do make our process. But it actually left open several questions about the origin of the elements. So we know they definitely do make our process elements. But first, are they the only our process site? And second of all, are they actually even important for cosmic nucleosynthesis? This galaxy over here, where this where this neutron star merger happened, is sort of a red, dead, elliptical galaxy. It has formed all of the stars it's ever going to form, basically, right? And so maybe because of these delay times, these neutron star mergers, they're just like exploding off in the middle of the nowhere. And so all of the R process elements they make, they're just like floating around in the universe. They never make it into stars or planets, right? And therefore, like, the R process that's like in the room around us, maybe it's completely unimportant for this purpose, right? So the way that people have tried to characterize this in the past is you can distinguish between core collapse supernova and neutron star mergers based on the time at which the R process happens after a burst of star formation. So core collapse supernova, they're the deaths of massive stars that happens essentially instantaneously after you form some stars in a galaxy. And so this, you form your massive stars, they die, and you make the R process elements. This is called a prompt source of R process elements. Neutron star mergers, in contrast, you have to form your two massive stars. They have to both die. They have to stay in a binary. And then the key thing is that they have to in-spiral through gravitational radiation before they merge and make those R process elements. And so there's a time delay between when you form your stars and when you create R process elements in this scenario. This is called a delayed source of R process elements. And so the thing that's been very interesting is that it turns out when you study basically the amount of R process inside of the Milky Way, it has been known for at least 2 or 3 decades that you actually don't need any source of delayed R process elements. Indeed, you cannot have a significant source of delayed R process elements in order to explain the R process composition inside of the Milky Way. The y-axes over here are basically the amount of R process relative to the amount of iron in the galaxy. I don't want you to, I'm not going to explain this whole thing. This would take a little bit too long. But the upshot over here is that as soon as you include a delayed source of R process elements, you end up with trends that are rising with metallicity as opposed to declining with metallicity. And this is just not what we see inside of the Milky Way. We knew about this by 2000. And people have continued sort of going back and forth about this fact. I think the most recent number over here is basically up to 50%, but no more, of the R process in the Milky Way can come from delayed sources. So it would be a relatively unimportant source for the R process on our planet. So I got interested in this question because we could study it with dwarf galaxies. And so our question we can ask is, what should we see in dwarf galaxies if we're comparing delayed and prompt sources of R process elements, right? And so this over here is a plane where each point on here is going to be one dwarf galaxy. The x-axis is the mass of the galaxy, and the y-axis is its star formation duration, the time to form 90% of its stars. So what should we see for the R process? Well, one of the things is if your galaxy forms stars for longer, it's likely that it should be dominated by delayed sources of R process elements, right? You form stars for longer, you can capture material from things that explode over a longer period of time. Whereas things that form stars for a very short period of time should be dominated by prompt sources of R process elements. And I just drew this blue line arbitrarily down the middle over here. In some sense, the question is basically like, where should we draw this blue line? And that sort of tells us something about the characteristic timescale for when R process is happening. So this is a useful thing. I think this is a little bit obvious. But the thing that's maybe less obvious is the stellar mass of your galaxy also matters. And this is because R process sources are rare. Indeed, they only happen about once every 100,000 solar masses of stars, right? If you form 100 solar masses of stars, you get a core collapse supernova, so multiply by 1,000. And what this means is if you look at low mass galaxies, when there's less than 10 to the 5 or 10 to the 6 solar masses of stars in your galaxy, you're actually dominated by the rarity of your objects, right? Like it happens, if you look inside of this galaxy, it's just going to be very stochastic. And so what you really want to do is you want to look at relatively high mass dwarf galaxies where you're not dominated by this sort of stochastic enrichment. This is nice if you want to study individual R process events, but if you're interested in sort of the time delay, you kind of want to look at the high mass galaxies. So every galaxy that we know of in the universe can be put somewhere on this plane, right? Like how long has it been forming stars, or did it form stars, and how massive is it? And the interesting thing is that when you compare it to observations of dwarf galaxies around the Milky Way, we don't fill out this plane. Right, so the lowest mass galaxies, they all quench relatively early inside of the universe, around 1 or 2 gig years after the Big Bang. That's because they're quenched by reionization. As you get to the high mass galaxies over here, these things basically form stars for the history of the universe, right? And so in some sense, this makes sense, right? Like, so there's like a hole over here, which is low mass galaxies that stopped forming stars recently. Like, why are they not higher mass, right? If they were able to if they kept forming stars over the whole history. And then the bottom right-hand corner also makes sense, right? Like if you're a high mass system, why would you stop forming stars? And so when you look at all of the intact galaxies in our universe, or in our local volume, what you see is that there's just a dearth of massive and short duration dwarf galaxies. But of course, there's a thing that can keep you, in some sense, as forming stars for a short period of time and relatively massive, right? And that's if you fall into the Milky Way and get tidally disrupted. So once you expand your scope of what type of galaxy you're studying to include the tidally disrupted galaxies, you now can study these relatively short star-forming systems that are relatively massive as well. And so for this particular study, we end up studying these two objects in the bottom right over here, which are the easiest to study objects. The other thing that's really nice about this is the stars in these tidally disrupted galaxies, because they fell in at relatively early times in the assembly of our galaxy, they're very close to us in the sun. And this is wonderful. When you study these red objects over here, their stars are like 1 to 10 kiloparsecs away, which is great. It's in the Gaia sphere. Whereas if you study these black points over here, they're about like 30 to 300 kiloparsecs away. Your life is just very painful. I've gotten converted over to studying these very nearby objects because we can figure out which galaxy the stars are coming from. So I want to focus on these two over here. There's two galaxies of similar stellar mass, but different star formation durations. One of them is called, so both of these galaxies were found essentially by doing 6 plus 2-dimensional searches. We see an overdensity of objects in some sort of conserved action angle space, or some conserved action space. And then we also find them as being distinct in sort of chemical space. I won't go through the details of how they're actually discovered. You can ask me about that later. This over here, this Gaia Sausage Enceladus, is probably the most famous galaxy. Apparently everyone knows about it, although you can tell me that later. But it's, this was basically the most, we think the most recent massive merger into our Milky Way. It happened about 3.6 gigayears after the Big Bang, which you can tell by counting basically main sequence turnoff stars. And it has a stellar mass of around 10 to the 8.5, 10 to the 9, depending on who you ask, of this. There's also another merger, which is a similar mass thing that accreted even earlier into our galaxy. It's called either Kraken or Heracles or something like that. It has a similar stellar mass, but it only formed its stars for 2 gigayears. And what this does is it sets up a nice natural experiment for understanding the R process delay time. This was realized by me and Rohan Naidu, who was a graduate student at the CFA. Now he's at MIT. And so I'll explain to you now sort of this natural experiment. So this over here, the x-axis is the magnesium abundance of a star, and the y-axis is the europium to magnesium of the star. I want you to think of the x-axis over here as the number of massive stars that have gone off in a galaxy before that star forms, right? That's what it means to have some particular magnesium abundance. Magnesium is primarily made by core collapse supernova. Then the y-axis over here is europium divided by magnesium. Europium is basically our R process tracer. It's not a pure R process, but you can tell if there is R process when you see it. And it's divided by the number of massive stars. And so the thing that's really interesting about this is that given a fixed place on the x-axis over here, eventually, if you look at all of the R process that ever gets produced in a system, the europium over magnesium should be the same, right? For the same number of stars you form, you should eventually produce the same amount of R process. But a different amount of that R process will get captured into stars based on the duration of star formation in that galaxy, right? And so to sort of illustrate this, let's imagine that the only thing that ever produces R process in the universe is core collapse supernova. What this means is whenever you produce magnesium, you basically produce europium. There is a substantial amount of stochasticity, but that's OK because we looked at galaxies that are so high mass, we don't care about that, right? So you should essentially have a constant plateau in the europium to magnesium ratios inside of the stars inside of your galaxy. On the other hand, if you have any delayed source of our process elements, if you have neutron star mergers, there will be a difference in the europium to magnesium ratio for these two different systems, right? And this is sort of a subtle thing, right? Because what it is actually these two systems will eventually produce the same amount of our process, but a different amount of it gets captured into stars, right? So in other words, in the 1.6 billion years between when this thing stopped forming stars and when this thing stopped forming stars, some number of neutron star mergers went off. Those elements got captured into the stars forming inside of this galaxy. And so these two things will differ. In other words, in that 1.6 gigayears, a whole bunch of neutron star mergers went off inside of this galaxy, but they just never made it into stars, right? I'm getting some blank looks here, so maybe I'll say that again. And so, what it is if everything is coming from core collapse supernova, you will always get the same value across no matter which system you study. But there will be a difference depending on the star formation duration of your system due to the fact that you capture more of that material inside of your stars when they form. So I've set this up very nicely now when we go out into these two different systems, measure the compositions of their stars. And indeed, it looks like this scenario over here. If you go to this GSE dwarf galaxy, which forms stars for a little bit longer, it has a higher europium to magnesium ratio than this Kraken dwarf galaxy, which forms stars for a relatively short amount of time. So we weren't definitely not the first people to say this. Everyone sort of agreed that this system had a large amount of our process elements compared to other dwarf galaxies. But they were comparing dwarf galaxies of quite different stellar masses, which means that you're folding through a lot of chemical evolution assumptions into those things. And anyone who's done those chemical evolution models knows how many knobs you have to turn for doing something like this. So I thought this was a very nice natural experiment that Rohan thought of that was very clear. I think clearly shows that there must be delayed sources of our process elements. Now, with this all said, I set up this very nice natural experiment. The thing that would be the best is if you could just go to this galaxy over here, go back to earlier times in the galaxy and see the actual amount of our process just go up with time, right? So the x-axis is number of massive stars. So the left is earlier in the history of the galaxy. The right is later in the history of the galaxy. If you can see this number just go up, that would just be the easiest thing, right? And until, as recently as 2019, people argued we have never seen something like this, right? You measure europium to magnesium in every single system that we go out there. The mean value is different from system to system. That's what I argued is evidence for the delay. But we've never actually seen this number just increase within one galaxy, which is the simplest prediction that you would expect. So we went out with Rohan and Xiaowei Wu, who's a graduate student at MIT, and basically just said, let's just find the most metal poor stars inside of this GSE system. This turns out to, and measure the R process content inside of it. This turns out not to be easy. I thought it would be easy, and it turns out not to be, which you can ask me about later. But we've done it. And so this is our new data over here, down to the most metal poor parts of this dwarf galaxy. And just looking at it by eye, you can see, OK, yeah, this number over here, there's a larger scatter, but it's definitely lower than this number over here, right? And so for the first time, we see the rise of the R process within this dwarf galaxy, Gaia, Sausage, Enceladus, which is basically exactly what you would expect to see if neutron star mergers dominate the R process production. Now, what I was hoping from this is that we would then be able to figure out, do you require any source of core collapse supernova in our process in order to do this, right? And so this is sort of two cases. The red one over here is just using neutron star mergers, and the blue one is sort of with core collapse supernova and then neutron star mergers. And the problem that you run into when you do this is that when you go to the early history of any galaxy whatsoever, all of the stellar masses that have formed go down, which means that you're stuck in that really stochastic regime again. And so it turns out that it's sufficiently stochastic in any model that you construct that this scatter over here is sort of allowed to be entirely, you can interpret this as, oh, there is a rise in this region that goes up to here, or you can interpret it as it is flat with a very large scatter and then rises afterwards. These are both allowed by the current levels of data. So, the obvious things are, let's get more data inside of this. This is what people are working on right now. But this is sort of the state of the being right now. We require neutron star mergers, but it is still unclear if core collapse supernova provide a contribution at early times. This all said, this is the current situation that we think when you look across the population of dwarf galaxies. This is sort of a toy model. There is potentially a plateau in the we don't see any plateau at the low metallicity end for any dwarf galaxy. We think this is in part because of just the stochasticity. But as you go to dwarf galaxies of longer star formation durations, they all have higher europium to magnesium. And indeed, and what this means in terms of like how important are neutron star mergers, inside of all of the dwarf galaxies, like anything that forms longer than sort of 2 gigayears, it's over 50% neutron star mergers. So at least in the dwarf galaxies, it's very clear that neutron star mergers are the most important source of our process elements. So before I conclude here, I just wanted to say that we did this study over here on these relatively massive dwarf galaxies going back to the lowest metallicities that we could study. But we're actually now going to every single one of these other dwarf galaxies and tracing them back to their earliest histories and seeing if we can see the rise of the R process. And indeed, so in this large Magellanic cloud, Anichidi and Enrique Reggiani have shown that basically we see the R process increase as you go from low to high metallicity. Guilherme Limburg looked inside a disrupted galaxy called Wukong, and he basically sees that also rise from low to high metallicity. And we're continuing through basically every single one of these other systems. We're basically expecting it to always go up now that we know how to identify the most metal poor stars in every single one of these higher mass dwarf galaxies. So that's sort of the takeaway here. Neutron star mergers pretty clearly dominate our process production in dwarf galaxies across the whole population. OK, I want to conclude quickly talking about dwarf galaxies of the future, sort of stepping back to the beginning and sort of where we're going to discover all of these different dwarf galaxies. So this is sort of a chart illustrating every dwarf galaxy that you could ever discover inside of the Milky Way's virial radius, right? We've talked today about intact, but in the midst of tidally disrupting galaxies. We've talked about sort of the intact classical dwarf galaxies and the fully disrupted halo contributors. So every time you do new deep wide photometry, such as the Vera Rubin's legacy survey of space and time, I think that's right. Every time you do one of these, do new deep photometry, you find new dwarf galaxies, right? And so we're expecting to find something between 50 to 150 more of these objects around the Milky Way just in LSST in the coming years. People are continuing to search for stellar streams, like dwarf galaxies in the act of tidally disrupting. We're still working on this. The challenge right now is almost everything is confined to within 50 kiloparsecs. We really would like to get outside of 50 kiloparsecs and search for galaxies in that region. But in the meantime, we can characterize all of the things within that radius. And then the thing that I'm most excited about is the thing which, in some sense, is the hardest. I would like to study all of the earliest tiny dwarf galaxies that are created and got completely ripped to shreds. We won't be able to identify which star belongs to which galaxy, but we at least can study that population of little dwarf galaxies as a population rather than individual dwarf galaxies. And this is really being brought about by the ability to do spectroscopic surveys and get huge number of chemical abundances for stars that could come from these dwarf galaxies. So this is sort of the next 5 or 10 years. I think we'll basically get every galaxy within the Milky Way's virial radius. But eventually, then we'll run out of all of those galaxies. And then what is the next step, right? Once you do that, then the only thing that you can do is just go out further. And to do that, you just need bigger glass, right? So this plot over here shows each point is one dwarf galaxy, one intact dwarf galaxy. The x-axis is how far away it is, and the y-axis is the luminosity of the galaxy. Right now, anything to the up and left of this dashed line over here, we can do high-resolution spectroscopy. This is basically what's needed to do our process studies. And so this, the galaxies I'm talking about are sort of in this region over here up to this region over here. That was what I did for that whole section. And if you do medium-resolution spectroscopy, which is metallicities and kinematics, right now we can extend this quite far, even out into beyond the Milky Way's virial radius. So the most naive thing that you can do if you build a larger telescope is essentially add 2 magnitudes to how deep you can actually go. And what that means is you can essentially do these R process studies out to the edge of the Milky Way's virial radius. And you can do sort of full chemodynamic studies all the way out into the rest of the local group. So I think this is where, on a 20-year time scale, where this field of studying dwarf galaxies in the local volume is going to go. So that's it. Gaia has been amazing for discovering qualitatively new types of dwarf galaxies and understanding them. I talked about galactic dynamics with this dwarf galaxy Antlia 2. And then I talked about the origin of the R process with this large accreted dwarf galaxy, Gaia Enceladus. I hope that at least some of this was interesting to you and that you will support studying dwarf galaxies inside of the future as we reach out to find these objects at any stage of tidal disruption throughout the Milky Way and into the local group. So thank you for your time. I'll take any questions.
I was thinking about observational evidence for R processing supernova. I remember seeing a plot quite a few years ago, and so I can't think of the reference now.
Yeah.
From pre-solar grains, and they looked at the xenon isotopes in some individual grains, and they saw that the P-process isotopes were correlated with the R-process isotopes. That, to me, suggests quantum supernova as the origin, because P-process is not made in neutron star mergers.
Yes, P-process would definitely not be made in neutron star mergers.
So that might be one place where, I mean, it's not astronomical observations.
Yeah.
It could be an interesting place to look. There's quite a lot of grains that have been measured, individual grains. And
This was xenon isotopes?
xenon isotopes.
Okay, cool. Yeah.
There are likely others as well, because they can do a lot with it.
Yeah, I've heard a lot about molybdenum.
But I think xenon, because those two,
Yeah.
I think it's clear it makes more sense.
Yeah, because xenon's in the second peak, or it is the second peak. And so that makes it a lot clearer of a test than the molybdenum, which people have been telling me about.
I'll see if I can find that reference for you.
Yeah, that would be fantastic. I mean, xenon is really hard because it's a noble gas, right? So there's all sorts of weird chemistry things that go into that. So I'm always worried about that.
But I think that's why they can see it in the nanosims, I think, because it is a noble gas. They can't, it's still there, it's basically still there in the grain. Yeah, so, and then because it's easy to extract out.
Oh, okay,
Because remember, this is done in an individual grain.
Yeah.
It's a lab measurement.
And they can do different isotopes in the individual grain of xenon. Oh, okay, I didn't know about that. Cool.
What fraction of vertical angular momentum in a disk is attributed to the LMC interaction?
Oh, that's a very good question. Right, so naively, you would expect that if you have something this big coming by and moving you, potentially it would cause a small-scale perturbation to sort of the vertical motions. I don't think at the current moment people think that it's that significant compared to something like Sagittarius, because the LMC doesn't actually hit the disk. So it's a relatively large-scale perturbation across the disk compared to something like Sagittarius, which just goes straight through it. But I'm not sure that people have, I mean, this is a simulation where they ran it, so you could, in principle, like look at the wiggles of all of those particles and find out. Yeah, I'm not sure.
You show the plot of europium over magnesium versus magnesium. Actually, unfortunately, magnesium is not really a good element to take as a reference one. Would you produce a similar plot with oxygen? You know, the magnesium, we cannot produce the amount of magnesium that we observe in the galaxy.
Yes. Yes. So we can't do oxygen. Yeah, it would be nice. So I would like to do oxygen every time so right now, the reason that people use magnesium is because it is close to oxygen, theoretically, and it's much easier to measure. Oxygen, if we know how to measure it in different ways, and each time you do it, you get a different result. And especially when you get to the metal poor end, it gets worse. And the systematics of each of those tracers, so there's forbidden oxygen lines, OH lines, and oxygen triplet. Yeah, they all give you slightly different results as you change with metallicity, and it's not clear we understand those systematics well enough to use for this purpose. This said, I think using magnesium in this context is okay. We don't know how to produce the right amount of magnesium, but as long as there is a true IMF integrated amount of magnesium, it's a fine tracer, right? We are not trying to run any models through this, and when we do, we just pick a number that fits the data, right? And so as long as there is a true magnesium production, and we're just misestimating it theoretically, this argument still holds. But this is precisely why I was very concerned about trying to compare dwarf galaxies of different masses and trying to produce models that explain this, right? Because you're starting with inputs which you're not sure you believe in. And so that's sort of the. So I think this statement is clear. If you go to lower mass galaxies, I would say you can't do this because then you worry about which mass star does your magnesium come from, and that is a whole concern. But these things are massive enough that you have many IMF integrations worth of it.
What you said, it will be true for oxygen because it's the result of the human burning. Magnesium is very tricky because magnesium is produced by the shell carbon burning. It's an hydrostatic product of shell carbon burning. So it depends on the carbon-12 alpha gamma. That may depend on the ratio adopted at the moment. But what is worse, it depends on the initial rotation velocity. So even within an IMF, you may have different results. It's really very tricky. I understand it's very easy to observe, but it's really easy, and the integration over an IMF does not preserve you from a change.
Right. So I would say that although this is true, so first of all, if your C12 alpha gamma rate is wrong, is different. It's going to be different everywhere, right? So that in of itself, from an empirical standpoint, of there is a true number. We don't know what the number is, but there is one number, right? The issue of rotation is a bigger one in the sense of you now need a larger, there's some initial mass function and some initial rotation function, and maybe they have some correlated parameters in that space, right? But as long as you sample enough of that distribution when you're creating your stars, you will converge to some total number, and then the concern is is there a substantial evolution as a function of all of this. Here I don't care, right? As long, if I'm forming of order 10 to the 9 solar masses of stars, I've sampled everything. And so even though you might have little wiggles and perturbations in the evolution, right? So I would say that this picture over here, where I've just assumed essentially a constant magnesium abundance that is produced by a core collapse supernova all the way through, this type of thing is very fraught with the types of things you're saying. But this sort of thing, where you're just comparing, stars from similar mass galaxies, similar high mass galaxies, so they're high mass enough to sample over all of these different things, I think this is actually quite robust, right? If you're now comparing the Milky Way to one of these dwarf galaxies, it becomes hard because then you don't know the right transformation between magnesium production from one and the other.
I didn't want to exaggerate, but also from this point of view, I have a comment actually. You are looking at the atmosphere world as a black and white. Either you have a fast timescale or a long one, but we live in a colored world in which you always imagine you have close encounters. So the timescale of the merging could have a spread of values. You may have a tribal system, 4 stars that, the massive stars form in a very complex way. So you may have a range of possibilities, not just a black and white.
Right. So I totally agree with this, and this is actually the rant that I go on every time someone like me gives a talk like this, which is that this association between prompt sources and core collapse supernova and delayed sources and neutron star mergers is a false equivalency, right? Because it tells a very nice story, but you can get effectively delayed core collapse supernova, right? What you do is you explode the core collapse supernova. They don't immediately recycle their metals, right? That's a huge assumption. They spew them out into the circumgalactic medium, and it takes time for that material to cool back. You do something like that, you essentially get a delta function in your time delay around a couple 100 million years. Conversely, yeah, you can have very fast neutron star mergers. People argue back and forth. Well, I don't argue with them, but people argue in front of me about how quickly neutron star mergers can merge, right? Some people say it can happen as quickly as like a megayear or faster, and other people say, oh, there's no way, we don't see short gamma ray bursts happening faster than 200 million years, right? So this, I would say, is, if I was being very fair in this statement over here, I would say delayed R process sources dominate R process production in all of these systems, which I think is fair. But yeah, so this is a very important point. I will say that we do include, both prompt and delayed sources of our process elements, and this is why we sort of want to push down into this regime over here, so where you can actually start distinguishing these things. But point taken, and I completely agree.